Hi there, welcome to this video. We'll see an example of how we deal with combined loads in transmission shafts that will result in transform stresses. Please check the other video that I explain the theory behind how to design transmission shaft, considering that it's subject to combined loads. So in the problem description, we're given the power information about the motor at point motor M, and we use that to figure out the torques throughout the transmission shaft. So we figure out in the main shaft we're analyzing here, shaft A, B, C, D, E. We figure out the torque that's applied at gear B, TB, and also figure out that the torque at both gears C and D are equal, and they're adding up together to TB to cause equilibrium here. And we are given allowable shear stress, and we are asked to figure out the minimum smallest shaft diameter that will safely carry and transmit these torques. So the first thing we will do is, when we consider now the action of combined loads, is we need to calculate the bending moments in the shaft. And to be able to calculate the bending moments, I will need to figure out the forces that accompany these torques, the TB and TC and TD. So I will have to calculate the force on the gear tooth at B and also at C and D, and I will do that by dividing the torque value at this gear divided by the radius of the gear. So FB is equal to TB over RB, FC is equal to TC over RC, and FD is equal to TD over RD. And I end up here with the forces, and I can show these forces on the free body diagram of the shaft, and also show them the reaction forces that are applied at bearings A and E. And I will assume here in some direction these reactions AY, AZ, and EY and EZ. And you can see here there is no axial loads or reactions along the length of the gear or the transmission shaft. And like we learned in the video that's part one of this lesson, we learned that we need to calculate the section that has the critical bending moments and also torque. So this is what we're going to do: find this location along this shaft that has the worst combination of T, moment around the Z-axis, and moment around the Y-axis, because these moments MZ and MY are the bending moments that causing flexural stresses in the shaft. So what I will do is I will develop the internal force diagrams for these three actions: the torque action, the bending moment action around the Z, and the bending moment action around the Y. And we'll start with the free body, kind of simplified free body diagram that shows every one of these specific actions. So starting with the torque diagram, I will show the shaft sideway and side view of it. And I will show here the torques, and you can see here it is already in equilibrium. It's not dependent on the bearings at A and A, because these bearings don't resist moments or torques. And I see that now I draw the internal torque diagram. It's pretty simple. The x-axis is going from the right end of the shaft, from the E end, and I start from this end. I see there is no action between D and E. And then I hit the torque 3,150 at D, and it's positive using my right hand rule. A moment, this is the thumb. If it's going to the positive X direction, it is a positive torque. So it's 3,150, and then I will add up another 3,150 at C. And then I'll keep going until B, and now I will hit 6,300, which is going negative. That will bring me to zero equilibrium. Now moving to MZ. So MZ is the moment around the Z-axis. So what I will do is I will look for the view of the shaft that will show the transverse forces relative to z. So I will look for, or another way is you look through the z-axis, and this will be the side view you will consider for the shaft. So this is what we'll do, is look through the z, which is kind of looking sideways here. Also, but we're showing here all the forces transverse that are in the y-x plane. So I'm showing here AY, I'm showing EY. I'm not showing FB and FD, I'm only showing FC, which is 788. And if you do the equilibrium, you'll find the reactions AY and EY, and you will be able also to draw the shear diagram. So I'm going up by AY, 460, and then drop by the 788 force FC to negative 328. And once I hit the EY reaction, that will bring us to zero equilibrium. And then we'll use the shear diagram to draw the moment diagram. So we'll not go in detail of how to draw that. That's part of your static knowledge background. So now I have the MZ diagram, and the last thing is the MY diagram. MY diagram, the moment around the y-axis, which means I will look through the y-axis. So I'm looking now from the top. So I have kind of a top view of the shaft. I'm kind of throwing it in kind of a 3D kind of view, but I'm looking from the top. And I see here I draw all the forces that are transverse to the y axis, or they are in the zx plane. And just to show you what we're talking about here, the axes. So the axes will be like this. The x is going this way, and then y is going this way, and then z is going this way. So anything in the x and y plane, in the x and z plane, because I'm calculating the moment around the y, I will draw these forces. So I have FB, FD, and I also draw AZ and EZ, but I will ignore FC because it's not following the description I just said, which is forces in the x and z plane. And then I will draw the shear and moment diagram for the forces shown here. But first I will have to calculate from equilibrium the reactions, which I did, and then I draw here the shear diagram. Using the shear diagram, I'll be able to draw the moment diagram. So now, done with all of that, now this is the most important part of that exercise, is figuring out really where is the critical section. So I can summarize all of these diagrams by saying that the maximum torque is happening at point B or C, any point along between them. The maximum moment Y is happening at point C. And the maximum moment Z is happening at B. So actually I'm switching here. Let me check here the values, just checking my notes. So actually, yep, so MY is happening at point B, the maximum MY. It's not, the writing here is not following the same order of the diagrams that I draw. So now I'm kind of split in between. I know that the torque is either at B and C, but one of the moments is maximum at B and the other moment is maximum at C. So what happens is I will have to consider both points, B and C, and trying to figure out what would be the one that will govern the design. And this is what we will do. So we'll do the internal moments at B, and remember from, again, part one of this lesson, we kind of summarized that there's kind of a resultant moment that combines both the bending moments and the torque twisting moment. So what I will do is I will calculate this value for both the sections at B and C. So if I do this at B, plugging in all these values here, the moments and the torque, and that will give us 9,000, around 9,000 poundage. Moving to point C, doing the same thing, and I'm plugging in the values from the diagrams that I did, and I end up with around 8300. Now, which one is critical? The one that gives us the largest internal resultant moment. So I can say here that this is more critical. And I will use that in designing my shaft. So tau max resulting from this resultant moment should be more than tau allow. And tau allow should be, this means here, tau allow should be more, again, that's another typo here, I will fix it. So that one here should be, tau max should be less than or equal to tau allow, which means tau allow is more than or equal to C over J. So that's basically the right side of the inequality here is tau max. Again, refer to the first part of the lesson. And if I plug in, I have all the values. I have the tau allow, and I have the moment values, which is the resultant I just calculated. And I will end up here with the least value of the radius, and this means that the diameter will be just double of that. So if we follow like usually, things are measured in inches, like 1 inch, and like increments of that. So you can say that the radius here is 1 inch, and the diameter will be around 2 inches. So you can see here that the actual strength of materials stuff, which is that second page here, it didn't take that long. The actual, most of the work that's done is based on statics. And this is why statics is very fundamental in this course. So you have to really get comfortable and master your skills you learn in statics and dealing with combined loads and drawing diagrams for all type of action and internal forces we're dealing with. Here in shafts, we need to consider all points in the shaft and pick the one that's most critical. So to do that, you have to draw the torque diagram and a diagram for each bending moment that's acting on the shaft, and then figure out. Sometimes it's just a clear call, and you just pick a one that has all the maximum values of my, mz, and torque. And in our case here, we didn't have a clear call, so we had to evaluate 2 points, and you evaluate them by getting that resultant of my, mz, and torque. Pick the largest, plug it in the value, and you end up with the radius and diameter of the transmission shaft. All right, that's it for this topic here. We'll see you in other videos. Take care of yourself and your family and those around you. See you.